So my name is Ryan, and today I will be talking about heat-assisted magnetic recording. So heat-assisted magnetic recording can be referred to as HAMR, or hammer for short. And essentially it's using heat to lower the anisotropy, and that will lower the required field to write to the bits. So this allows us to use a higher anisotropy material for bit stability while lowering the required field for us to write, which makes it way easier to write. Okay, so why is hammer important? So first we can talk about aerial recording density. So aerial recording density is the amount of data you can store per square inch on a disk platter. And then we want this to be higher because as we have more data demands, as AI grows, data center grows, computing grows, we need more storage of data. We can like increase the amount of HDDs we use, or we can use like SUT or STT MRAM, but those are like expensive options. So we want to lower the cost per storage. And the best way to do that is through increasing aerial recording density. And this can be done with hammer. So looking back in history, the first demonstration of a magnetic recording happened by a Danish scientist in 1898. So he had this idea of taking a steel wire and attaching a trolley to it. And he would use a telephone transmitter and receiver to record his words and also play back his words by sliding it down the steel wire. And then fast forward to the 1900s, in 1947, that was when 3M released the first commercially available tape. It used like an iron oxide to write data. And then in 1957, that was when the hard disk drive was released by IBM. And that was the first hard disk drive commercially available. And that uses a iron oxide, just like the magnetic tape. Okay. Now, fast forward to the modern day, there's actually two types of storage we use for mass data. It is a magnetic tape and HDDs. The problem with magnetic tape is that it's not random access, so we can't use it for like online computing and stuff. So HDDs are like the preferred choice. And then, so let's talk about the different improvements in HDDs. So this is how we got to hammer. So initially, we used longitudinal magnetic recording. And the reason for this was because if you align the magnetization in plane, then it makes it much easier to sense the field. But the problem with this was that we had this repulsive force with nearby bits. So it became unstable at higher densities. But with the introduction of like giant magneto-resistive heads and TMR, that made it possible to have perpendicular magnetic recording, where the bits are aligned perpendicular to the plane. The problem with this was that there wasn't repulsive force, so that's a good thing. But the bad thing was that the magnetic field that we sense was so low that, and back in the day it was impossible, but with GMR and TMR heads, that allowed perpendicular magnetic recording to happen and allow us to have a higher aerial density. And then fast forward to, I guess now, with perpendicular magnetic recording, the aerial recording density is reaching its limit. So we need to increase the anisotropy to have a higher aerial recording density. But the only problem with that is that it makes it much harder to write the bits. So this is where hammer comes in. So with hammer, it consists of a heat sink, TMR head, laser, nano-focusing structure, and a use of a high anisotropy magnetic media. So how it works is that you have a TMR head, which is pretty typical with modern PMR HDDs. So you would use a laser. It will provide a heat source to heat the bit we're writing, and that like lowers the anisotropy and AC field required, and that makes it much easier to write to the bit. And then as the bit cools, it returns to its normal operating, anisotropy at room temperature, and that makes the bit stable. And it's pretty interesting here. You can actually see this is also the typical structure with PMR for the right head. But you have a coil, and then it provides a magnetic field to write the bit, but there has to be a return path, and we have this return path right here. But how does these bits not be written? And then I was wondering that, and then I found out it's because if you go back here, we have this soft magnetic underlay, and this actually like disperses the magnetic field back. So like these bits won't receive a high enough magnetic field to like get its bits written over. Yeah. So looking at the materials, a typical PMR media uses a cobalt-based alloy like cobalt, chromium, platinum. You can see here the anisotropy is pretty low, and then the required field to write to it is around 3 to 10 oersteds, which is like 0.3 to 1 Teslas, which is pretty doable. But hammer uses iron platinum. That's like the typical material. The anisotropy here is around 5 to 10 megajoules, which is pretty high. But the downside is that the required field is like like 1 Tesla to like 3 Teslas, which is pretty high, and that's where heat comes into play to lower it so we can write easier. So the physics behind hammer, there's three physics that we learn in class that applies. Is ferromagnetism. So we use this concept because we need to retain the magnetism to record the data. We can't use para or diamagnetism, that wouldn't work. And then we also use the concept of anisotropy. We use that, we want a high anisotropy material to keep the bit stable and prevent it from flipping. And then lastly, the third concept we use in class is temperature, the temperature relation between anisotropy and corrosivity. So we use temperature to lower the anisotropy and corrosivity to make it easier to write. Okay, so going through breakthroughs, what made hammer possible was the founding of the near field transducer. So this is made by Challenger team in 2009. So basically, at that time, the light diffusion limit was like around in the hundreds of nanometers, and with hammer, with such a small area recording density, you need like a very, very small diffusion optic. But the only problem, that wasn't possible in 2009. So, and then Challenger and his team, he found out that using a near field transducer, he can like reduce the size of the diffraction down to like 15 nanometers or 25 nanometers, and that made it possible to use hammer for higher area recording densities. So you can see here, you have a laser, it produces around like a diffraction light around in the hundreds of nanometers. And then going through a near field transducer, it can be reduced down to like 15 nanometers, which is sufficient for a hammer. Okay, so going to the next breakthrough that made hammer possible is the read head. So when HDDs were made, the inductive read head was used. How it works is that there's a coil, and as it passes through the bits, it will detect the changes, and then that's how you would like record the bits. But the problem with this was that it provided a very low sensitivity, and that's the reason why longitudinal recording was used. And then with the introduction of the MR head, that provided a higher sensitivity, but which is great for increasing the areal density. And then GMR heads came in around like 1997, and then that allowed a higher sensitivity, which allowed for perpendicular recording. And now we have a TMR head, which uses electronic tunneling, and that has an even higher sensitivity, which allows for us to have higher area recording densities, and that also allows hammer to have, to work. Okay, so going to the last part, the weaknesses. So these are some papers I found. Vlogger in 2016, he released a paper where he actually did some research with the switching probabilities. So he found that when you heat bits near the Curie temperature, it's not deterministic that the bits will flip. He actually found that it was probabilistic. So that basically means that if you increase the temperature, the grains that you apply the heat to in the magnetic field, it's not guaranteed that all of them will flip at the same time or the same temperature, like always. So that was kind of like a bummer that made it seem like hammer may not be reliable as other methods. And then Bargava and Jablonowicz in 2014, they published a paper studying the near-field transducer, and they found that the transducer may not be as reliable due to the stress of heat damaging the material. And then lastly, there's this article from Albuquerque, Hernandez, Keith, Murray, and Rain. They actually found that past 4 terabytes per square inch, the read head that we have, the TMR head, may not be able to scale as well, and we need a better head to be able to read it. Okay, and then lastly, for future directions, first of all, we can see that the near field transducer and TMR head allowed for a higher aerial recording density, which made the vision of hammer possible to where we are today. And then for future direction, we can look at bit pattern magnetic recording. So that's where instead of like having grains, we have like well-defined magnetic islands. And combined with that, with hammer, there's like clear boundaries, and that can like help improve the aerial recording density. So you can see here, this is like 1 bit with multiple grains, whereas with well-organized islands, each one of these can represent 1 bit. And then also another thing you can look at is heat-assisted SOT membrane. That's where you use joules current to like heat the device, which makes it way easier to flip the magnetization. And yeah, that concludes my presentation. So thank you.